All right, so we're going to start on chapter 10, hypothesis testing. So this chapter can seem a little bit overwhelming, but I give you a template you use to do the problems, and it makes it all just step by step by step you do the problems. Okay, so focus on the big picture. Okay, chapter 10. Let's get started with the introduction. So a hypothesis is a statement we make about the parameter. Remember, the parameter is the population, and we're trying to understand the population. A hypothesis test is a procedure we use to test hypotheses using sample data and probability. I'm just getting the chat open, so if you guys have any questions, and I have the participants list open, which you can use to raise your hand as well. Okay, so we're going to start with two examples, one for the mean and one for the proportion. According to a Nielsen Company audience report, an adult person in the United States spends approximately 10 hours and 39 minutes each day on screen time. This average of 10 hours and 39 minutes, or 639 minutes, includes our daily use of smartphones, computers, video games, radios, tablets, and TVs. It's believed that students at your community college spend more time on screens each day than 639 minutes. Students in your class use a survey that asked 25 students to record their screen time, and they record a mean screen time of 655 and a standard deviation of 41 minutes. Is this unusual enough to provide sufficient evidence that the screen time of your community college students is more than that recorded for adults in the US? So our data is higher than 10 hours and 39, but the question is it high enough to say, yeah, I think that data does not apply to our community college? Second example, hypothesis test for the proportion. According to the national census, 24.5% of all US residents who live in renter-occupied housing units lived elsewhere 1 year prior. Because needing to move while attending school is believed to negatively impact student success, your community college decides to learn if the rate of moving is less for its students. A random sample of 1,004 students results in 228 who have moved in the past year. Is this unusual enough to provide sufficient evidence that the rate of moving for your community college students is less than the national rate of 24.5%? So the outline for hypothesis testing, you don't need to write this down. There's 4 steps. 1, make a statement regarding the population mean or the population proportion. 2, collect data and compute the sample statistics. 3, analyze the sample data to assess if the data is sufficient to make a conclusion. And step 4, state the conclusion. We're going to start with analyzing the sample data to see how we do that, to assess if the data is sufficient to make a conclusion. In hypothesis testing, we're looking to see if new sample data indicates a difference or a change from current population data. So we're looking for a difference or a change. The statement that there is no change or no difference is called the null hypothesis. Null meaning nothing. So there's no change, no difference. The statement that there is change or difference is called the alternative hypothesis. So that's the alternative that we're claiming may be true. Before trying to determine whether the sample statistic is far enough from the population parameter to make a conclusion of change, we have to define the level of significance we're willing to accept. What does far enough away mean? So here are some of our definitions. The level of significance of a hypothesis test is determined by the researcher and is denoted by alpha. So that little symbol, alpha. It's the level at which we're willing to accept an incorrect conclusion that things have changed because we happen to have collected a sample that is extreme. The critical value of the variable is determined by that significance level. If our sample falls in the critical region, then it's extreme enough to conclude there is a difference or a change. The test statistic is the z-score or t-score for the mean or proportion of the sample estimate. StatCrunch will calculate that for you. So if we're looking at this picture, we have alpha that our researcher gave us. It's usually 0.01, 0.05, occasionally it's 0.10. And that alpha is this area to the left, in this case, in our picture. This is our critical region where that area is. We have the population mean here, which is mu sub x bar or mu sub p hat. We have our sample. If our sample falls far enough away that it's in this critical region, then we're willing to say there's a change because it's far enough away from the population mean. If it's not far enough away, then we're not willing to say it was a change. It's possible that was just a low sample, but it's not low enough to say there was a change. And the researcher decides what low enough means. So that will be given to you. The p-value of a hypothesis test is the probability that your random sample is so extreme that you would be making an incorrect conclusion to say things have changed. Okay, so I like to think of the p-value as the probability that you're wrong if you say things have changed. And you don't want to be wrong. So it's just based on your sample and your test, you would land here with either your p hat or your x bar. And that defines this p-value. Oh, that's the wrong way. There we go. So to perform the analysis of the hypothesis testing, we ask if the p-value is less than alpha. If the p-value is less than alpha, then my p hat or my x bar is far enough away. So if the p-value is less than alpha, we reject that things are the same and accept that there is a change or a difference. So is the probability that my sample is just high or low less than the chances I'm willing to take? That's our question we're asking. Because alpha are the chances that my researcher is willing to take. So if the probability that I'm wrong is less than the chance I'm willing to take, then that means the probability of being wrong is small enough, I'm willing to say that things are different. So let's look at the 3 types of hypothesis tests. We may expect the sample to be larger or smaller than the parameter, or we may not know if it's larger or smaller, and we just want to say that it's different. This leads to 3 types of test: left-tailed, right-tailed, and two-tailed. Let's look at an example of a left-tailed test. So here we're trying to show that a population parameter is now less than before. So maybe we're looking at the mean and we're saying, I think the mean is lower now. So that's why we have a left tail, because we're looking at things that are smaller. We expect our sample data to be smaller than our population data. So the critical region is in the left tail. This area is alpha. And we reject the idea of no change or difference if the probability is less than alpha that a random sample statistic is less than or equal to our sample statistic. So we're looking at less than on the left tail. The right tail is the opposite. We're looking for a sample that is much higher than the population mean. So it's a greater than picture. So it's on the greater than side. And sometimes we don't know which side we expect our data to fall. We just expect it to be different. So we use what we call a two-tailed test. So now our rejection area has 2 parts, the left tail and the right tail. So as you begin conducting a hypothesis test, you want to ask yourselves these questions. What's the population parameter you're trying to determine? In our case, we either do a proportion or a mean, but there are other kinds in other tests. What's the required level of significance? Again, that's set by the researcher, so you don't have to figure it out. It's set right there for you. And then is the test right-tailed, left-tailed, or two-tailed?